Good afternoon, everyone. How are we all doing? I hopped in a little early today for the lecture and just sort of stopped in via the text chat there. Summarize it for anyone who wasn't necessarily reading. Text chat's already gotten pretty busy. People are talking about challenge exercises in the tutorials and labs, and discussing not necessarily how to do them, but even just the merits of doing them, and just like what's the deal with doing incredibly difficult content like that, and maybe even why am I leaving that content there. I should point out to everyone that the challenges are not necessarily intended for everyone to complete. If you look at them and you see something interesting in them, even if all you see in them is like, I know that I can do some stuff that's pretty basic. I know that I can do some of the lead-up exercises that are obviously aiming towards that. So Order 3 is a question that then becomes more advanced in the challenge exercises. The spiral question is one of the grid drawing things. So you've got a grid of things and you draw stuff in it. That gets more complicated if you want to. But you don't have to. Sometimes it's actually good enough as a kind of even just a thought exercise for you to look at it and go, okay, I can see that this goes deeper. And I think that I mentioned this at the very beginning when we were starting learning about learning about learning. Sorry, I was like, learning about what am I going to talk about? Learning about learning. That's what tripping over my own words. That learning is equal parts understanding things and patience. Knowing that the human brain's only going to process a certain amount of stuff at a time, and knowing that you're going to choose how much stuff is going to stick in or isn't. That's the kind of thing that that sometimes the challenges are enough to get you thinking about the future. For some people, the challenges might be the present. And for everyone it's going to be at a different time, so it depends on your pace and where the course is. So I think I just want to remind everyone that the content of the course is not time limited, especially stuff like challenges. You don't have to do them now. They might actually be really valuable to you in 6 months' time or something like that, and you might go, I've got these techniques now that I've learned in other courses and stuff. Maybe I can come back and apply these things. Or even not even that, it might just be I've done harder stuff now. Everything I did in 1511 was pitched at a beginner programmer level, and now I've done harder things. Let me go back and look at those old things, and you may find this wonderful kind of thing where you go back and look at these old things and you go, I can do that. I think that was like one of the funniest things the first time that I supervised an exam, and I was I think I was a fourth year engineering student at the time or something, and I supervised a prac exam for first years, like this course, and I read through the exam on the bit of paper that had been given to everyone. So they actually gave them the exam on the bit of paper, and then they had to do the exam on computers, and it was very, very interesting because I just scribbled in the margins and I completed the whole exam in, I think, half the time that the other students needed to do it. And I was like, I wasn't a good student, I was a decent student, but I wasn't someone who even bothered doing most of the challenge exercises and stuff like that. But time and training and practice got me to the point where I could do things like that. And so I think that one thing to remember when people are talking about challenges and doing all this hard stuff, that you don't have to be there. It's not super important. You may get there by mistake later on, then you'll look back and go, hey, I'm pretty good at this stuff. This is great, And allowing that to happen, having the patience to have that happen, is potentially much more fun, So, that's what I was going to say. Don't put too much pressure on yourselves. The world's going to put a lot of pressure on you anyway. So just let that happen later, and for the moment, understand that if I'm going to put something in a challenge, then it is not something that I want people to take on pressure to have to complete. Because that's the whole point of the challenge. It's outside of the things that I'm already putting pressure on you to complete, which is the actual lab stuff. Anyway, hi Tom, welcome. Tom Killingback today is our moderator. Did I mod you? I did mod you, yeah. So you now have mod status. So the next thing he types should be highlighted, I think. Right. Yeah. I won't go too deep into what's happening in chat. I know there's going to be a lot of stuff in chat, so I think, yes, Tom's name is modded now, so you'll see the blue name means that there are replies happening. Okay, so let's get into the lecture itself. Talking about what we covered last time. Last time we were talking about code style and code reviews. So we were thinking about how to write your code so that humans can understand it, and this includes yourself, obviously. We're all humans, even me. I am not robo-lecturer. People always have this idea that the lecturers are just like switched off when the lecture finishes, and then like they just turn us back on to deliver the next lecture, and we don't actually have lives outside of that. But yes, we're humans too. So techniques for trying to make sure that our code is always kind of at a standard level of readability. So there were really easy ones, which is just like follow these rules. That's fine. And then there were things that were talking about how we work with other people. So code reviews, doing sort of collaborative programming, as well as having your code looked at after the fact, which is the kind of thing that you can actually do when you're working even in tutorials and things like that. There may be opportunities during term. The tutors will decide themselves depending on how much time they have free, but there might be opportunities for you to actually volunteer code to have your class look at, which is kind of cool. Okay, and then we looked at functions. Obviously we have not, I don't think we've looked at functions enough to really understand them yet. You've had an introduction from me of some of the syntax of the functions, but what I might show you today are some bits and pieces that that show you how functions can be useful in certain circumstances. Okay, so today I want to talk a little bit more. I've hinted at this previously about the theory of what a computer is. I broke it down into really, really simple parts, which is like, you know, the thinking part and the remembering part. And we're going to look a little deeper at that today. We're going to get you a little bit more educated on what's physically inside the computer. It's not too deep, right? But it will set you up to then go on later and learn more things about it. As this is an introduction to computer science, well, I guess it's like, what's it called? Introduction to Programming Fundamentals. So this is an introduction to computer hardware, which is why I'm only really going to spend like 20 minutes, half an hour on it today. You want to get really deep into computer hardware, there is the possibility to do that, but I'll just show you. This is like I was talking about in chat earlier. I'm trying to put you on a path, and you choose how far or how hard you want to walk on that path, in a sense. I'm going to show you another path here, which is the path into computer hardware, and you can choose how far and how much further you want to go into that. You could pivot your entire computer science, computer engineering style degree into really just learning about how to work with hardware at the closest possible level to hardware. You can totally do that, but that's not for everyone. So I'm just going to show you the start of several different paths in this course, and then see where you go on them. The other thing we're going to cover today, so it's not all just a path that a lot of people may not go down. There's another part of this. This is a path that everyone's going to go down, which is learning about arrays. Arrays are very, very useful. They're something that allows us to use multiple variables at once in a collection. And I'll show you why that makes sense, and then we'll work with them a little bit today. So today's demonstration at the end of the lecture, I'm going to do some stuff with arrays, which are groups of variables. I'll just keep explaining them in different ways. See, I'll show you like how they work before we use them. But we're going to use arrays and functions. So we'll write at least one function. So I'll show you how I would write some code, and then I would think, oh, this code looks like it might get used more than once. I might put it into a function, so I only have to call it, and then it'll happen again. So hopefully that'll give you enough demonstration on both of those things to get a decent idea about what's going on. Of course, everything that I cover this week is going to be in the tutorials next week as well. Okay, so what is a computer? This is something that I've spoken about a little bit before, which is just the question of when we think about it theoretically, because we can think about it physically. If we want to think about a computer physically, there's a whole lot of stuff in there that we don't fully understand. So I'm not sure, I very much doubt that anyone here has a full working idea of how mechanically and electrically memory stores information, or how mechanically and electrically a CPU actually executes the instructions that we ask it to do when we write code. So we're not going to think about it quite at that level, but we're still going to be thinking about it with some knowledge of the fact that there is hardware, but a lot of theoretical ideas about the way it fits together, the way we can think about it, and how it relates to us using C. So, there's a processor. The processor executes instructions. So it's kind of the thing, it's not exactly like this, but it's the kind of thing that's going to read our code line by line and say, I'm going to do this, then I'm going to do this, then I'm going to do this, then I'm going to do this. Ooh, it's an if statement. Let me check some information, then I'll decide whether or not I'm going to do the next bit, you know. The other thing that a computer has is some kind of memory that holds information. I used memory with a lowercase letter here, processor with a lowercase, because I'm not getting too deep into the exactness of these things. It's more about thinking about how they work. So when I say memory that holds information, there's actually lots of stuff in the computer that holds information. We'll talk about that in a sec. I want to talk about a theoretical idea. This is the thing called the Turing machine. I told you about Alan Turing in the very first lecture. Alan Turing was someone who worked a lot in computing in the 1940s, and he was the one I was telling you about who helped build the systems that cracked the German naval codes at the time and allowed the British to get a leg up on the Germans in World War II. So this was a theoretical idea of what a computer was capable of doing. So it had a piece of tape that was infinitely long. So basically think of it as a piece of paper, this really long sheet of paper, and then a head, which was something that could look at places on the piece of paper and read or write to them. So you could read or write. This is basically like us going through memory and reading or writing ones and zeros to it, basically. So the head can then move along to any part of the tape, and it also has a state. The state is it knowing what its current status is, and knowing which instructions it has completed previously and stuff like that. And there's also a set of instructions which is like, if you see this situation, then do this. If you see this other situation, then do that. So this is the entire model. And given these capabilities, so if we have an infinitely long piece of tape, very similar to the way we lay out our memory in a programming way, something that can look at one bit of it at a time, and they can move to any bits of it, and also remembers what it's up to, and has a set of instructions it's going to follow. The very, very interesting thing about the Turing machine is there is nothing else that our computers are capable of doing, and I'm talking about theoretically, computationally way, capable of doing, that isn't covered by this. So it's very, very interesting that such a simple idea of just moving around in something that records information and then reading and writing from that is all that we're doing. And that's really all that we're doing. And you may have noticed that a lot of our programs, that's all that they're doing. We're setting up pieces of memory that are like integers and doubles and stuff like that, and then we're changing the values in those things, and we're jumping around between them. And we have this idea of like, okay, we're going to do a sequence of things, and we know what those instructions are, which is our code. So one of the most interesting things about this is this theoretical idea predates most of the digital computing era. It predates the invention of bright-colored LEDs and things like that. Yet, having done that, whether or not we have created all this new hardware and all this stuff to be able to work with computers, this system, we haven't actually created anything that can do more than this. Like, this, of course, whatever this is takes longer to get there because it's a theoretical idea. If you had a machine that was going to move along on paper instead of digital things, it would still be capable of doing the same calculations by the end of the time it took to do it. So we've got a couple of images of Turing machines here. So I took these from Wikipedia, and this is a really complicated one that's looking at using magnetic tape and rollers and motors, and so it's got really like clear ideas of what it's doing here. So it's moving this magnetic tape along, and then all you're doing is like looking at stuff and then either deciding whether you're going to write a 1 or a 0 in each of these spaces. And then you have this idea that if you read the symbol, you have this idea you will do other things based on that. One of my favorite things, though, and this is one of the easiest ways to think about it, is you're a little person in a box, and you can drag the box back and forth through space, and when you look down, you see 0s or 1s written on the floor underneath you. And then inside the box, you've got written a set of instructions like this, which is like, okay, if you see a 0, do this. Otherwise, if you see a 1, do this. If you've read along a series of things and you saw a certain sequence of 0s and 1s, then you do something else, you know? And we could put a little person like me in this box and just have me having to walk back and forth following these instructions. But eventually, I would be able to compute everything that our computers can compute. So I think these are funny ways to think about it, because when it boils down to it, computers are very, very simple machines. The complexity comes into how much stuff we ask them to do. Because they can do it so fast, we just keep piling work onto them. And the more stuff we pile onto it, the more complex it gets. And then we try to give a computer enough work that it can keep working for, I was going to say minutes. Like, none of your programs in 1511 are going to run for minutes unless you make a mistake and you've got an infinite loop, right? But we have programs that have been running for, weeks, months, years, and we've given them enough work to do that they can do that, but all the work they're doing is as simple as moving around and changing 0s to 1s or vice versa. That's all that's happening. We complicate it, we add more context to it and stuff like that, but really, that's it. So I just think this is a really wonderful and interesting thing, this idea of Turing machines, because it means that, no matter how big or complex things get, when it really boils down to it, all you are doing is reading or writing 1s and 0s to something, and then following a set of instructions. So, let's boil this down to some of the things that we know and some of the things that we're kind of working with when we're working in C and with our computers. So, the processor. So I said there's two things, processor and the memory. The processor is something that we would often call the CPU. So, every computer, every smartphone, a significant percentage of fridges and home appliances all have CPUs in them. So this is a thing that is basically a maths machine. There's not much else going on there, but it's a machine that does some processing with numbers, and it's usually all based on 0s and 1s. There's other stuff than that, but really when it boils down to it, it's all 0s and 1s. So the CPU is going to remember the state, and it's going to follow the set of instructions, and then it can do some reading and writing to and from memory. This is actually not physically what the CPU does. It doesn't access the memory itself, but it sort of does. We'll talk about that in a second when we talk about memory. So when we're thinking about C programming, we can see that our state, so the current state, place that we're up to, is where you are in the code line by line. So as you're going down the lines of code, sorry, I just saw like a possibly, I don't know why that was moderated out from Deluxe. It's a question about the difference between a CPU and a GPU. I will, if you're, actually I don't think that you can make the prerequisites for it this year, but I'm going to be teaching computer graphics, and that's where you'll learn the difference between a CPU and a GPU. I'm not going to teach it here, it's way too much. the CPU, the state, we can think of this as, if we look at all our lines of code, we're up to a certain line at any point in time. And then if we're up to that line, it means we're going to execute that line and move on to the next. So we know where we are, where we're up to, based on what line we're up to in the code. And you can really follow your code by going, okay, we're going to do this, then we're going to do this, then we're going to do this, that kind of thing. And the set of instructions that we would have had in a Turing machine, these kinds of instructions are actually the stuff that we've written. So the code we've written are the instructions that the process is going to follow. And then the reading and writing, so the changing of the ones and the zeros. If I'm in my cardboard box and I'm walking along and I want to change a 0 to a 1, I might have a piece of chalk or something. So I'll rub it out and then I'll draw a new thing with my piece of chalk. When we're doing that in C, all we're doing is assigning new values to variables, or we're reading the value out of a variable to do something with. So we start to see how, at the basic level of what we're doing with programming, it's the same thing as the Turing machine. It's just a little bit more complicated, and also, in a way, easier to do more things at once. So if I gave you just a piece of tape in ones and zeros and I said, take two numbers and add them together, the instructions for that are actually really complicated, because you've got to be like, okay, you have to advance through 32 bits of stuff and then read those 32 bits, and then knowing that we're going to encode those bits into an integer in a particular way, then you have to do something, and then you have to go to another set of 32 bits, and then you have to do the same kind of encoding thing, and then you have to have some method of combining those two numbers together to add them up, right? So it's all very, very fiddly, whereas in C, we're just going to put the plus sign between two numbers, right? So yeah, so that's what our processor is doing. Then when we think about memory, so a lot of the time when you're buying a computer or something like that, you're going to get told about memory. That's going to be talking about a specific part of the memory on the computer, because the way that we separate it when we're buying and selling these things is we separate them based on physical components. So one of the physical components is the memory that we call random access memory. RAM, on average, most of the computers that you and I have are going to be somewhere between sort of 4 and 32 gigabytes worth of this memory. But we're also going to give hard drives, and hard drives are also a memory storage. You know, they're just a different kind of memory storage, but they're still just memory storage. So when I'm talking about the theory of memory, all of these things are memory, but they have different purposes. So the hard drive tends to be much, much bigger than the RAM. So this, you know, I've got like a terabyte or two in here, as opposed to a few gigabytes of this. So we're looking at roughly 1,000 times the storage, but you also get roughly 1,000 times the speed of being able to move data in and out of it as we come up to the RAM. And then we have another level of this, which is stuff that's actually physically on the CPU itself, which we call the CPU registers and the cache on the CPU. And if we want to, there's lots of little distinctions in here. Like we could split up hard drives between SSDs and spinning platter disks. We could go beyond hard drives and go to tape storage backups and all this kind of stuff. But like, I'm trying to keep it at least manageable. So I've only split it into 3 levels here, whereas this is actually 2 different levels. But let's not get too deep into this. So this stuff is very, very small. Couple of megabytes, and this is the stuff where your instructions will come out of the RAM and go in here and get run and then get bounced back and stuff like that. The trick and the difference between these is this scale here. The faster something is, the less of it we can generally afford. So your CPU, to store a few megabytes of information, is going to cost, I don't know, $50, $100 or something. I'm making these numbers up, by the way, but in order of that, 50 to $100 worth of hard drives is going to probably store, I don't know, 100 to 200, not 100 to a million, 100,000 to a million times more data than what was on the CPU in the cache. So we get this kind of difference, and the only reason we have all these different kinds of memory is this stuff's cheaper, and we need to store more stuff. So there's heaps of things that are going to go in your hard drive that are not necessary for your CPU to store. The other thing that's nice about your hard drive is out of these 3 levels at least, this is the only one that remembers what it had in it when you turn your computer off. I was about to go, so if I turn my turn my computer off, yeah, then the stream will die. So if you turn your computer off, there's a bunch of stuff that's saved. So for example, your C files and stuff like that are saved in memory, in your hard drives. But everything that you had, your currently running programs are in RAM, and the very current program that's running right now would be here. All of this stuff will be like, oh, we're just going to flush our memory when the power goes off. You know, when we start up again, we're full of zeros, and then we'll slowly load stuff in from here. So you get this kind of thing where it's going to be used differently based on whether it's a more permanent storage for memory. And then when it's faster and smaller, it will only be used for those things that's really, really necessary and current. So yeah, these are the different levels, and it's a long scale, and there's lots of other stuff going on. But I don't want to go too deep into the details. I'll tell you how C uses memory and how it uses these different levels of memory, because we don't really need to know all the levels of the memory and stuff like that, or details of hardware specs. We don't need to know any of that kind of stuff to understand how we're going to use this with C programming. So let's talk about C and what it does with these things. So C files, our source code files, will be stored on the hard drive. So this means that you can save a file you're working on, you can turn off your computer, turn it back on again, and then you can just keep working on the same file, so long as you saved it. So any file with a .c on the end you've been working with, you may have noticed that you can go away and come back and you can keep working on it. This is a reasonably understandable thing, I think, for our computers. We know that this kind of stuff works. We can also use DCC. So DCC or other compilers are going to translate your C file into something that you can... Basically, the idea is the executable program is something that you can like double click on and it'll run, that kind of thing. So DCC will transform... Well, not transform, it'll translate this into another file that is also stored on the hard drive. So after we've run DCC, we have 2 files on our hard drive. One which is the human readable instructions, and the other is the machine executable thing, which is the program. So we've got those 2 pieces. We've seen this. Not sure if everyone is like fully on board with this yet, so like explaining it again just in case. So we've got those 2 files, and they'll always sit on our hard drive. But then in our RAM, random access memory, when we run our program, and not until we run our program, the instructions, so everything that's in this file that gets compiled, the executable program, are going to get copied into memory. So they get copied into faster memory because there's going to be a lot of stuff that's going to read and write to it while it's running. And then our CPU, this is where we start working with both pieces, not just the memory, but the processor as well. The processor is going to regularly go into that piece of RAM and go, ooh, what are the next few things you want us to do? All right, we're going to grab all that stuff, bring it onto our smaller, faster storage, work on it there, and then send stuff back to memory only when we need to. And so when we're doing stuff like we're changing variables, they're going to go back to our RAM and they're going to store it there. So C has a particular... I remember this slide. This slide's super busy. So there's not much space for my face in this slide. So I'll just do that. And I'll change the angle of this a little. So this is the actual layout of a C. Well, it's not to scale or anything, but this is the way that our memory will work when we run a C program. So when we do / program name, so / dice check or something like that, this structure gets constructed in our memory. So our operating system says, oh, okay, so you want to run your program, so I need to give you enough space in memory so that you can run the program. So it's like, okay, here's a chunk of memory, you can run the program. I'm just ballparking figures here. You usually get about 2 gigabytes of memory, and then when you ask for more, the operating system will give you more. If I remember correctly, the limit that most operating systems, and you'll see it, I think if you ever use that much memory, which is unlikely, but if you ever do in VLab, I think VLab says you can have 8 gigabytes of memory, and anything bigger than that, you're going to have to do something special with your program. So operating system gives us some memory, and our program then copies everything it needs there. So it'll actually do this kind of thing where all of the instructions that are going in the program will be copied in. Then after that, any of the variables that the program knows it's going to need that have been declared in the code are there. The current state will be stored at the opposite end of the memory, because the current state's actually going to grow and shrink depending on where you are. It's not actually as simple as a single kind of line number for where it's up to, but we'll talk about that later. Too much at once. And then we have this empty space in between, which we call the heap, and the heap is where random pieces of things are going to appear when we ask for more memory when we're running our program. So we have not used the heap yet. We have a vague idea of what the current state, the stack, is here. We don't need to know about that too much. The instructions you should know because you're writing them, and the variables you should have a decent idea about because you're also writing those. So this is how the program looks in memory. By the end of term, you're going to have used all of this. So you're going to find out ways to use this space called the heap, and you're going to find out what's actually happening on the stack. But it's really not until the end of term that we really get too deep into that stuff. But at least this gives you a look at some of the stuff that goes on. So I'm gonna stop this little introductory tour of computers and operating systems and stuff here, and say this is a very, very quick overview, and there's a lot more that goes on. So when you start to think about it, you go, okay, the Turing machine is just like ones and zeros, and you can read and write ones and zeros. But then we're writing C, and C doesn't write ones and zeros like explicitly. It allows us to work with numbers and stuff, and I can say, just give me a number variable in integer. And this thing's already doing 32 ones and zeros, and it's also identifying what it can do. You can use random things like plus symbols and divisions and all this kind of stuff, and it just works. So that means there's all this stuff under the hood that's happening to get you to that, between that kind of Turing machine level of capability all the way up to what C is going. There's all these layers in between, and it involves memory management, processor management, and all this kind of stuff. So I just wanted to let you know that this is part of what goes on in the background. Some of you may have heard of some of this stuff before. I think basically everyone who's using computers will have at least heard the terms CPU and RAM and stuff, because someone somewhere has tried to sell you a computer because of XYZ CPU that's in it, or XYZ amount of RAM, or the RAM's faster on this one, or like, all this kind of stuff. And like, a lot of the time we just buy stuff and it's like, I don't know why this is better. I don't know if this is definitely going to be better than something else that I could buy, but I also don't have the time to research it. So I'm just like, okay, it's a computer and it will probably do what I need to do, right? And then only once you get really deep and you spend years learning about this stuff, you go, oh, okay, I do actually understand the link between these things, what different memory is, and why it's important to have good memory at multiple points in that chain, and what your processor is actually doing, and how your operating system interacts with those bits and pieces. So many courses in CSE will take you further down this path if you're going to continue and look further into it. But for the moment, I think hopefully what I've done with that very brief kind of half-hour little talk is tell you more about how your programs are actually linking up with other parts of the computer. So hopefully that just kind of gives you a bit more context for how your computers are running. Okay, what are people talking about? Not too much there. Ooh, Lorenzo's saying I've got the wrong title on the stream. Yeah, because what I do often is I copy the stream from the previous year or term and do it, so I'll fix that later. Okay, so let's talk about arrays. Arrays are actually, I was going to say, it's amazing because the talk I was doing before about memory leads directly into this, and it's like, yeah, that's because I wrote it that way. Sometimes Passmark actually plans these things. Okay, so sometimes we want a collection of variables together. Sometimes we want a big chunk of memory, not just a little chunk of memory, or lots of little separate chunks of memory. Sometimes we need to process a lot of variables of the same type. And what we know at the moment, what we've learnt so far about ints and doubles, might not be able to deal with being worked in batches and groups very well. So let's have a look. I'm gonna justify what we're doing here by looking at what we're capable of and then what we can do to add to it. So let's say I write a C program that is going to record everyone's marks. So what it's going to do, it's going to have an integer. It's actually more detailed than that. This is obviously not the program that we use, but let's just say I've got an integer which has the marks for each one of you as students. So the variable name here might be your ZIDs or something like that. So I go, okay, I got the integer marks of the ZIDs for everyone in the course. And then as things go on, I'm going to change these integers. So every time one of your labs gets marked, I think lab 1 has been marked already. Lab 2 definitely won't have been marked yet, because what we'll always do is like finish the lab, so the due date will be on the Monday, and then some people have extensions and we mark it afterwards. So it's usually going to get marked sometime around a week after the due date. Yeah, so every time something gets marked, these will then get updated in some way. I obviously don't have code for that here. I'm just talking about how I declare it. Lorenzo says something's behind me. Is this code incorrect? I don't know. Maybe you're thinking about, you know what's coming next. Right, that's good. Okay. So if, I'll just move my screen, just my face out of the way of the text there. If we wanted to test these integers, so if I wanted to say, who's passed the course? Wait, something about parentheses, someone was saying. I think maybe I didn't initialize anything and I didn't close those brackets and stuff, but that's alright, this is just partial code. Anyway, I'm gonna go on, not gonna get distracted by that. Okay. You're probably right, and you've probably seen something that I haven't seen yet. Okay, so let's think about this situation. I've got all these variables, each one has a different name, and I am going to test who has passed and who hasn't. So I've brought etceteras in here because there's over 900 of you, so there's gonna be more of these. And then I'm gonna check if student 1 is over 50 and then they pass. And then is student 2 over 50, they pass. There's no way to loop this, because I can't do a loop that checks a different variable every time it goes through the loop. Because there's no way that in the loop I can say, okay, check this variable name, now check a different variable name, now check a different variable name. That's not possible, right? That's not part of the syntax that we know for how loops work or anything like that. So if I was going to loop through these, I can't change the name of the variable that I'm accessing in the loop. So there's just a slight thing missing here that I can't do. And there is no way I want to copy paste the same code 900 or so times, especially because this program would then only work for one term. And then the next term I have a whole bunch of people with different ZIDs. I'd have to just delete the whole lot of them, create a whole new set of integers with different ZIDs and stuff like that. So not feasible, right? Too much work. It feels physical. You know, it feels like we're physically doing too many things at once. So we don't want to do that. So let's think about how we might want to do this a different way. So what we're going to do now is we're going to use arrays instead. So, sorry, I just saw a chat there, Jordan's like, don't want to copy and paste a lot of if statements. Word addition, hold my beer. That's a good meme. You should make that to a meme and chuck on the forum. I will use that. Because this is the reason why word addition is in there as a challenge in the early part of the course. It's so that when you reach this, you understand what the limitations were with the code previously, and then when we start doing better things with it, we can do more interesting stuff. Okay, so let's use these things called arrays. So instead of the integers being individual integers, we're going to collect them and access them as a group. And so if we're going to be able to access them as a group, we are going to be able to combine that with loops, and we're going to be able to loop through all the bits and pieces that are in it. Now, I'm going to show you the technical side of this so you understand how this works, and then we'll go through some examples. We'll do some programming in the second half to show how that works. So, here's an array. We're thinking about it, getting closer to the actual C code for it. So when we have a single variable, I've said when we had a single variable, like an integer is 32 bits of memory, or a double is 64 bits of memory. You will learn about other variables very soon, and they will have their own memory sizes and stuff like that. Whenever we declare one of those, our operating system that's running on our computer will go, okay, here's the memory you need, and now we know where that memory is. That memory is going to be in that section of memory for variables, because our code instructions have been read by our operating system and said, oh, okay, you said you were going to declare these variables, so we've assigned this space in advance for you. So if we knew where our program was in memory, we could actually find those variables. For us, from a C perspective, we just go, oh no, it's got a name. So we're going to use the human name for it, and we're going to trust our computer to find the right location for it. So declaring variables is something I think we have a reasonable understanding of now. It's just creating space to store information. An array is really interesting because instead of having an individual variable, you can actually declare a chunk of space that contains multiple of the same type of variables. So here we have a single integer worth of memory, and then we have an array of integers that holds 5. Like, it doesn't have to be 5. You can actually say how many you want when you declare it. And so each one of these acts like an individual variable. So each one of these is an integer, but as a collection, they can be thought of as one big variable that contains multiple other variables. So it's interesting because when you create the array, it gets a name, but the individual members of the array, the individual elements as we'd call them, they don't have their own separate names, but they have a number which is like, oh, I'm the first one, I'm the second one, I'm the third one, that kind of thing. So you can see this now, right? You can kind of see this because our while loops are very much working on a number. Every time we loop through, we can change a number, which means we could loop through these now in a way that we can't loop through these. So let's get some of the nitty-gritty going. Let's get some of the understanding of how we're actually going to build these in C. When I declare an array, it is actually reasonably similar to declaring a single variable of that type. The only thing that happens after we give it a name, so we give the array a name, we then have these square brackets. And square brackets are the array symbol. So every time we see square brackets, it's going to mean there's something to do with arrays involved. So we're going to use these to create them, and then the square brackets are going to be used later to use arrays as well. So the first thing that's going to happen if we're going to create them is we put the square brackets directly after the name, so we say this is the type, these are the types of variables that are going to be stored in it. Arrays can only store one type of variable, so I can't have an array that's like half ints, half doubles. There are ways to do that in different kind of what we call data structures, and I'll teach you some of them later, but for the moment, when we're using arrays, they all just contain one type. So this is going to contain multiple integers, and I've put in the square brackets here the number 10, saying I will store 10 integers in this array. The only thing that gets a little bit more complex when declaring an array is this weird stuff that I'm doing here, which is the initialization. So you don't always have to initialize an array. You could, if you want to, go, okay, this is just uninitialized data, which is potentially dangerous, but you can do it, and you go, I'm going to fill this in later. We did this every now and then when we did scanf, where we said, oh, I've got an integer, and it doesn't have a value until I do scanf, and then it gets a value. So integers can do the same kind of thing arrays can do the same kind of thing where I could leave out this equals bit on the end here. And it would be a little bit less safe, but it would still be legal and still be potentially functional. But what I'm going to do here is show you, this is probably the default way to initialize an array, where I put in curly brackets here the list of things that I want to put in the array. If I put nothing in there, all of the array will become zeros. But if I want to, I can actually put stuff in there. So I could put a series of values, or they could even be variables that you take the value from and stuff, and it would store all of these in the spaces for the numbers here. So I've said, okay, I've got an array that has 10 spaces for numbers, and I give you 10 numbers, and it's going to put them in. So it's going to take, the first one's going to be equal to 0, second one equal to 1, etc. here. Or I can initialize them all as zeros. So there's a few different ways of doing this. I actually have a code demo that shows you another thing that happens, but that's a bit of a subtlety, so I'm not going to bother talking about in the lecture. You can dig deeper if you want to. But I'll show you the demo maybe in a second. I'll see how I'm doing for time. I'm watching the clock, because I know that the code demo today is a bit long, so I will probably try to use the majority of the second half on that. Questions? I see Tom's answering most of the questions there, so yeah. People are asking about Python, and people using lists and iterating through lists in Python. Yes, this is going to be a little bit similar to that. If you don't know Python, don't worry. I'll just teach you how we do it in C. You don't have to know anything about Python. Okay, so when we're looking at... that's hilarious. I just need to... Yeah, there we go. Sorry. Sometimes when I make a little mistake in my slides, I have to fix it before we go on. Okay, so each element of the array. So we consider each of these individual numbers. So now we're getting more detail here. So I've put values in for each of these rather than previously where I said, okay, they can store something. Now we're going to put values in here. So we go, okay, these are the students' marks. So it's looking pretty good for a lot of people. Some people maybe need to put a little bit more work in because they haven't finished everything yet. Smarty Pants over here has got 91. So if these are the students' marks, this is where people are up to. Each one of these can be accessed as if it is an integer variable. You know, it may be a part of the array, which is like one big container variable, but each of these can be used as if it's a normal integer. So as long as you can find it, and that's the interesting thing, so long as you can find it, you can treat it exactly the same way as you'd treat any other integer in anything that we've done in our coding. That goes the same for doubles as well, or any other variable types that we may put into an array. So they're accessed individually by an index, and the index is how far away they are from the start. So the first element is 0 distance from the beginning, so it's at the very beginning, so it gets 0. So basically this number here is telling us how many of them to skip over to find the number that we're trying to access. So if I say student marks index number 3, that means skip over 3 values and then get to this one here. That's a simplification of what's going on. Later on, I will tell you a little bit more about that, but that's only after we've learnt a little bit about what direct manipulation of a computer's memory is. But this indexing is how we're going to use our arrays, and like nearly every time we're using arrays, we're going to be using this kind of indexing. So the only thing to remember is that 0 represents the first element, and then size minus 1 is the final element. And then you'll kind of get the hang of it as it goes along. So now that we have seen all of the theory of how this works, I'll show you some code, because there's a potentially confusing thing here with the square brackets. So I said the square brackets are the symbol of the array, and so they're going to be used to both create the array but also access the array. So this little piece of code might look really similar to this little piece of code, but they're actually quite different, because this one is the declaration of the array, and the declaration of the array says that this is the size of the array. But after the array has been created, we won't ever be able to change its size. So once it's declared, it's a chunk of memory that's a specific size, and it can't grow or shrink. So that's something that that we need to remember, because it's going to become important anytime we're not sure how much information we need to put in something. We need to make it a certain size. Maybe we'll have to make it bigger than we need just in case, you know. But for the moment, let's say I only had 10 students. I don't think anyone in 1511 only has 10 students, because all of the tutorials have more than 20 people in them. But let's just say a theoretical world where I teach a course that is so weird and esoteric that no one really wants to do it, and I only end up with 10 students. We'd probably cancel the course. But anyway, if I had 10 students, this would be their array. And so what I can say is, let me take the first element of the array. And so we get these square brackets again, but they do a different thing this time. So now that the array has been created, and I'm using it, I'm accessing it, what I do then is I use the square brackets again, and I put in an index. So this is the index. So student marks 0 is equal to 85. So what I've just done is I've seen student marks 0. So the square brackets allowed me to jump to an index. This happens to be the first one. And let's say this person who was on 55 before was remembered to submit the second assignment or something like that. Or we hadn't marked everything that they had, and so we'd marked everything, so their mark goes up to 85. So this is exactly the same as if I'd created an integer and I'd done an equals with an integer. So if I do an equals with an integer, that assigns the value to the integer. So this assigns the value 85 to the first element, because 0 is the first element in this array. So that's one way we can do things. We can also access elements of the array using variables. So if I have a variable that's an integer, that integer variable can be used as an index into the array. So you're starting to see this, right? There's a reason why I just taught you looping and now I'm teaching you arrays, is that when we loop through, we're going to loop through. And remember how we were like, how I was saying, like, the loops start at 0? The loops start at 0 and the arrays start at 0. So we end up with a cool situation where if we just use the loop counter, we will be able to move through an array and we'll see all of the elements in the array. So remember we did a loop from that was going to go through 10 times? It was going to start at 0, it was going to go to 9, and when it hit 10 it wasn't going to loop anymore. So if I had code inside that while loop that went from 0 through to 9, each time that loop ran, it would run being able to, if I used the counter as an index, it would look at a different element of this array and will look at all of them exactly once each. So looping and arrays, very, very joined together. They will work together heaps. And we will, most often when we're working with arrays, we'll be writing loops, because we'll be like, oh, I just need to look at everything in the array, so I'll just write a loop. So that's the standard loop. That was the first loop I showed you, which is the one that ran a specific number of times. Works really well with this. Someone's asking about, does array -1 still refer to the last element of an array? No, if you use -1 as an index, it'll try to go here in memory, and then it'll say, whoa, that is not an index of this array. We've got a problem here. So I've got actually a little bit more information here. So as I said before, anything that accesses an array using an index will be treated as an integer, which means you can actually do things like copy one element of the array over another element of the array. So this could be very good or very bad for student number 2. If student 6 copies over student 2, ooh, that was good for student 2. So the 62 would overwrite the 44 there, because it would read from this one and write to this one. Same way as the normal use of the equals, but now we're getting another level of kind of possibility of what we can do with it, because we can access different elements of the array. If we try to access an element of the array that is outside of the array itself, we're going to get an error. Most often this will be called an array out of bounds error, but you'll see it when it comes up. Actually, we can do some demos, and I can show you what happens when it comes up once we're writing code. So I tried to give the index 10 student, which is actually the 11th student, a mark of 99, but what actually happens is index 10 does not exist in this array. It's off the end here. So all I did was try to put 99 somewhere where I don't actually have access to write that memory. So it will probably throw up some kind of error. This is a little insidious because this error is not likely to come up until you run it. It's a kind of error that's probably not going to appear when you compile. Right, so that's a lot of things we can do using code to use arrays. This is still scratching the surface. We're going to get deeper into this when I do a demo. So, interesting thing about doing stuff with printf and scanf. So printf and scanf are things that that we'll do with variables quite happily. We'll be like, okay, read in this variable, write out this variable. But they can only do things with individual variables. So there are things where we can't actually call printf on the whole array and expect our computer to be able to like separate each of the elements of the array and write them one at a time. We also can't scanf a whole array at a time. So what we need to do is we need to leverage the fact that we can do it for individual elements, and we also know how to loop. So if we can do it for one thing and we can loop through all of the things, that means that we have a way of doing it for everything, and we don't have an easy way to do it for everything. We'll have to do it ourselves. So if I'm going to try to do printf and scanf, I could do this kind of thing where I put a 0 in there. That's still going to make everything all zeros. I can declare an array with all zeros here, and then I can say I need to put new user input into the third element of the array. So the third element of the array is index 2, and I'm going to say scanf an integer and throw it into the third slot in the array. So you can definitely do this, because this here, because we've accessed using the square brackets an individual element of the array, this puts us in a situation where this is treated as an integer. So I can put the and in front of it, and I can scanf a number into it. I can output the value of a single element as well. So I can say, what is the fifth element? Sorry, it's a movie thing. There's a movie called The Fifth Element. It was really, really famous years and years ago. So we could do this thing where we can say, take the fifth element from this array, so index 4 is the fifth element, and then write its number out like that. And the important thing to think about is this code won't do it for you. So you can't just go, I have student marks of size 10, I want to scan in 10 separate integers and then dump them all in here at once. So the print also, if we had printf here instead, that also wouldn't work. So that's the one thing that we need to think about. This code doesn't directly work. We'll need different code to make that work. Okay, so we're just about halfway through, which is good, because I want to spend the second half just coding and showing you how this kind of stuff works. So let me move my face out of the way of this hilarious diagram. So last week we were talking about code style and things like that, or even before that we're talking about problem solving. We're trying to write code that is good code. I mean, it's really hard to even describe what good code is. Like, is it code that you're happy with? Is it code that functions correctly the majority of the time? Is it code that doesn't necessarily have all the functionality, but you know you can modify it again in the future? Is it code that other people understand well? So it's always really hard to decide those things. And this is a hilarious joke from a webcomic called XKCD. So XKCD is a very, very technical webcomic. The more you learn about programming things, the more things in XKCD are going to become jokes that you get, in a sense. So it's like, yeah, there are all these ways to code, and it's like all of them end with, no matter what you do, they all end with throw it all out and start over and then come back again. And there's this question mark for how anyone ever gets to good code. All right, 4:59 now. We will come back at 5:04, so we'll take precisely 5 minutes break, and then we'll go on to showing you a little bit of code about how we use arrays. I actually have some demo code in the folder already, but yeah, we'll write a program that's going to use arrays, and we'll probably do at least one function in this as well to show you how we're going to do that. All right, back soon. Hello. I'm back early because someone came to say hello. Hello. We're still officially on break time, so you can have a little bit of cat time until it hits 5:04, and then I'll start coding again. Unfortunately, the microphone was off when she started meowing at me to say, hey, I want to sit on your lap. Okay, back to work, chicken. You go back to whatever it is you do for work, which is usually sitting somewhere. Okay, off you go. Right. I opened this up, but we're not going straight into code just yet. I'll go back to my slides. So, let's think about people always ask me about my keyboard. We'll talk about my keyboard later. You can stick around after class and we'll talk about the keyboard again, because we had a lengthy discussion about this after one of the other lectures as well. So, I have, for the first time in this course, a program that is not based on dice, but it's still based on games, because I love games, so there's going to be games. So, we have players playing a game, and for this one, it's going to be a 4-player game, and we want to be able to track the players' scores in some way, and we also want to be able to print out the scores of the players in the game. We want to be able to see who's winning the game at the moment, and the game is, let's say the game is some kind of semi-cooperative game where the game also wants to know how many points have been scored in total amongst the 4 players, right? So what we're going to do is make a program. I haven't written any code for this yet. I mean, a lot of it's in the slides, so I could always just read that out and type it in. But it's going to be a program that's going to be score tracking. So keep track of... Sorry, someone's laughing at the t-shirt. Yeah. Keeping track of the amount of points that each of 4 players have. And I'm going to show you a little bit as we do this about how we might make this more useful if we were going to use it in the future. So, for example, we could do something where it's not actually limited to the number of players. It doesn't have to be 4. I could do something where it could be a different number than 4. We're also going to at least throw 1 or more functions into this so that we have some kind of generically useful functions that can be good for arrays and things. One thing I did want to show you... We're in lecture 6. I did have a file in here already. So I'm just going to paste the link for today's live code. I mean, the only code in there currently is a demo, but live code will appear in there in a second. So someone was asking in the break about the subtleties of initialization. I just tab completed this. This is one of the best thing when there's only one file in the directory. You don't even have to type anything. You tab complete and it goes, you must mean this file. Okay, so having a look at the arrays demo that I've shown there actually shows you some of the subtleties of initializing. So I wasn't talking about this in the lecture because it's not going to come up that often. Most of the time we're going to initialize empty or initialize full. But if you initialize partially full on an array, what it does is it puts these numbers in the first 3 slots and then fills out all the rest with zeros. So I can show you this, and this is an uninitialized array here because there's nothing there and there's no code to fill it out. So I'll show you this running. I think that this part of it won't do anything, but I actually have made a function here that prints an array. So this function takes in an array and takes in the length of the array. So it depends on what array I give it. I can give it a different length to work with things. This is going to loop through the array, and for each element in the array, it's going to print out the number that's in there. So it's assuming an integer array and then a space. So it's just going to print out what's in the array. And we can see here that I've called this function 3 times here. There's a 4th time here that's commented out. That one's to show you that there could be an error here if I tried to print an array that wasn't initialized. So I can print these 3 arrays. And so the first one is empty, second one's initialized 1 through to 10, third one is initialized 1, 2, and 3. So I'm going to compile this. Just call it arrays demo. Ooh, warnings. Ah! So I'm getting a warning about the unused variable array4, which is correct because I've created it to show you an uninitialized array, but I haven't actually done anything with it, which is fine. I also have an array index out of bounds. So this is very nice. A lot of compilers won't tell you, but this is saying, hey, this is an array of size 10, and you're trying to index the 11th element in size 10. This is probably not going to work. So if I run this, I'm quite likely to have this crash on this line, but we'll still get to see some of this stuff working before then. So the interesting thing is, if I've only got the pink things, the warnings, I can still run this program, but the warnings are trying to tell me that something's wrong with it. If I have red things here that are errors, then I won't be able to run the program. The errors would mean it doesn't compile. The warnings means it does compile, but you need, like, the computer's like, yeah, I'm going to compile this, but you need to think about this. Something's up here. So if I run this, there you go. I got my crash there because I tried to access an uninitialized variable. But before that, I printed out the 3 arrays. So first one was the array initialized with an empty list. So that comes out as all zeros. So anything I don't initialize in this list becomes 0. And then I have the exact 10, and I get the exact 10 there, so these actual values will get stored in the array. And then here I've stored 3 values in the array, and it'll go, okay, I'll put those in the first 3, and the rest of them I will make 0. So this is nearly like I've given it nothing, so it's put nothing in, and then it's made the rest of them 0. And then here you can put some in, and then it'll make the rest 0. It's not going to get used that much, but, you know, thought I might as well show it anyway. Okay, back to what we're actually going to try to achieve with the with this score tracker program today. Let us, before we jump into the code, before we jump into the code, we want to think about making a plan for what we're building. So let's break this down into parts. So what are the individual pieces? I shouldn't have said elements here. Elements are individual elements of an array. It's always funny, the keywords that are programming keywords, if I use them in English, they may not mean the same thing. So, first thing, we're going to create an array. Alright, so we know that we're storing scores in this thing, so we need an array. We don't know if it's doubles or integers. I'll probably use integers because most of the demos I give you are just going to use the simplest thing, which is integers, and I won't use doubles unless something really specifically calls for it, like those percentages and stuff that we did. Right, and so if we want to access the individual players, we're going to need to use the indexes. So we're going to have basically players 0, 1, 2, and 3. And we may leave them as players 0, 1, 2, and 3, even though we know that most of the time we would think of this as players 1, 2, 3, and 4. But for the moment, while we're in a programming mindset, we're going to start counting from 0. It's really funny. You can tell programmers out in the wild by people that start counting from 0 instead of 1. So we're also going to need somewhere in this, we're going to need while loops that go through the array. So each of the things that we're doing, if we wanted to display the scores, we're going to need a while loop that goes through and displays the scores. In fact, I've already closed it. I actually had a while loop in the demo code that prints out the contents of an array. So we may be able to use that exact function. So we'll see how we go. If we want to see who's winning the game, we're probably going to have to loop through and see which score is the highest. If we want to see how many points have been scored in total, we're probably also going to have to loop through and add them together. So I'm going to show you some of the simple things that we can do with looping through an array of numbers. Okay. Yeah, And as I said here, most of the functionality is going to be done by looping through the array. So let's get this started. We're going to create the array, and then we're going to we're just going to manually populate this with some scores. I think these are the exact scores that were in the array previously, but when we do it in code, it might not be exactly the same, because I'm just going to be making it up as we go from here. So it's going to start a new file. I think score tracker is a good name for this. This is an arrays demo. Track the score of 4 players in a game. Also, have functionality to find the winner, highest score, as well as the cumulative total of all players' scores. My name, you would put your ZID here. You can actually just use your ZID in your UNSW email, which is different from this, but you know. And we are in March 2021. Good. Okay. I know that I'm going to need my standard input-output because I know that at least one of my things that I had to do was to be able to display the scores, so I need to be able to print stuff out. Oops. I've got my main. Alright. Here's my standard setup. This will start a program for me. So, one thing that I'm going to do, I don't want the number 4 to be prevalent all through my code as the size of my arrays and the amount I'm going to loop and stuff like that. Instead, what I would like to do is use a constant for that, using a hash define, and I'm going to call it num players. And so this is 4 now, but the cool thing about this is I can write a whole lot of code, and every time we think about the maximum number of players, it's going to use this thing num players. And then if I want to change the number of players in a future version of the game, so let's say I want to release some DLC for my game, right? Because I bump my game up, and there's been requests for being able to play with more than 4 players. I can say, all right, I'm going to release my DLC, and the only thing I'm going to change in my DLC is this number. There you go. Now it's an 8-player game. Good luck. Have fun. Yeah. So the cool thing about this is all the rest of my code, anywhere that it hinges on the number of players, is going to use the hash define for it, which means it'll be very, very easy for me to change the number of players if I want to later. So this is why I like to do this kind of thing. Anytime I see a number in my code that I call them magic numbers. If there's a magic number in my code that is going to control the operation of a whole bunch of stuff, it's better in a hash define than it is just as a raw number, because then I can make changes later and stuff, and also it's easier to read. Okay, so the first thing that we need is the array itself, and we're defining scores, I think, as integers to keep it simple. So it's going to be an array of scores. Not sure if I'm going to initialize it or not, but I know exactly how big it's going to be. It's going to be as big as the number of players. And I think I will do this basic initialization. And as we saw a second ago, if I don't give it anything, it's going to fill them all out with zeros, which is fine. Player scores can start at 0, and then as they play the game, their scores may increase. To make it easier on ourselves, well, I think I had a counter for a loop somewhere else. We're not going to put that here. I think we'll put that somewhere where we're actually going to use it. Let's make it easy for ourselves by assigning values directly to the indexes. So I put a 0 in there. The 0 is unnecessary. So that's like I set the first one as 0, and then I let the initialization set all the rest of them as 0. Sometimes I will put a 0 in there just to remind myself that this is making everything 0, because this is something that... Oops, 0. This is something where I look at it and go, oh, it's 0. But then if I do this, I should probably be able to remember that the empty brackets is going to make everything zeros. Okay, so let's manually enter the scores just so that we have something to work with, because we don't necessarily have a mechanism for that yet. Because we could add that mechanism, but what I really want to do is show you working with these things as if there are scores already in there. So I want to access an individual element. I can go, the first element there is equal to, and then I can give it a number. I'm just going to put random numbers in by mashing the keyboard. And then I can go to the second player. Second player's winning by a lot. Third player. Ooh, okay. I pressed a lot of keys that time. These are integers, so I'm actually like, there's a long, there's a big ceiling on how big these integers can be, so I'm still pretty safe with that. Okay, so I've just got these numbers here that are the current scores for the players. So obviously different from what's in the slides, but it doesn't really matter, because all we're looking at is the fact that these are integers and we're going to be working with them in some way or another. People are joking that I'm EA. It's actually, I think, on my channel. If you go back through my old videos, there's a talk I gave for CSE SOC about the history of video games. History of computer games? Video games. I think it's video games. Not all games are on computers, right? And I go on a rant about EA destroying development companies in that video. Okay, so here are my scores. And now I have an array, and my array will be populated with numbers. So, here's my array. Here are the chunks of memory for the array, and this is 95, this one is 907, this one's 1567, and this one is 732. The indexes for these are 0, 1, 2, and 3. So we're going to hang on to this diagram. We will be coming back to this whenever we make changes or do things, so I can just kind of draw what's happening as it happens. Okay, so we've got this. Let's go back and see the first thing that we might want to do is to print out all of the players. So we'll print out their player ID, which is their number, I guess, which would be 0 through to 3, and how many points they currently have. And so we can do this quite easily in a while loop. So I'm going to set up my iterator as 0. Let's make sure I'm working on my code somewhere where it's not going to get covered up by my face eventually. Okay, so I've got I equals 0 while something. What I want to do is try to use, the standard set of things that a while loop has before I put my code in it. So I have a variable that I'm working with. I have a check to see where I'm finishing. So the check is going to be I is less than the number of players. And then I've got my iteration, which is the thing that's going to move me through. So it's nearly, I don't know if anyone ever does this, but if you're into recording macros and stuff like that, so people do this for games and stuff where they record one button press does a whole series of things. You could nearly record something like this. Probably this condition wouldn't necessarily have this hash defined in it, but you could record this and go, this is my loop, and just press one button and the loop will always look like this, and then you edit it for your purposes. So that's something that I could see people doing if they wanted to. Okay, so I know that this loop is going to go through all of the players. At the moment I know there's 4 players. So for each player in the list, I'm going to do a printf, and we're going to say player number something has a certain number of points. And it's going to be player number I, because I is the thing that changes as we go through the loop, and it's going to go through 0, 1, 2, and 3 through the scores. And the second number we're going to point out is that player's current score. So we're going to look into the array and use I as the index we look into the array to extract the variable from it. So scores I. Remember, first time we use square brackets for an array, it tells you how big the array is. Every time after that, after the array is created, the square brackets allows us to access one element of the array. So this is the 0th element, and then the second, well, so it's the first element at 0, second element, third element, fourth element. Likewise, as we're looping through, we're going to go through the elements one at a time, like this. So this is going to print out the current scores of everyone in the game. Someone was asking, maybe for human readability, we could actually do I+1 here. So, suggestion there, I'm happy with that. We can totally use that if we want to. So we can actually start calling these players 1 through to 4, like this. But we're just going to have to remember that every time we display it to a human, we're giving them numbers 1, 2, 3, and 4. And every time we're thinking about it in the array, we're using the numbers 0, 1, 2, and 3. Actually, you know, because usually I do like to take all of your suggestions. I'm actually thinking I won't this time, because I think I want to reduce the confusion as much as possible. So there's only one numbering scheme. So we're going to use something that's, yeah, not that great for any human reading this, but for us learning about coding it, I want to keep it with the zeros. Yeah, so I hope you don't mind if I do that. So we're going to go player 0 like this. And so let's save this, compile it, and run it. And what we're hoping here is this while loop will go through each of these 4 scores and print them out. Hey, Alvin. Alvin's one of the other tutors hanging out today. So let's go score tracker. Oops. And we'll call it score tracker. And we'll run our score tracker. And we'll be like, oh, cool. We get, I know I shouldn't sound so surprised when my code runs, but it did run. And it's gone through the first one and said player 0 has 95, player 1 has 907, player 2 has 1567, and player 3 has 732. This is a good point. So we can see in our program right now that this code that we wrote to enter the information worked, and this code that we wrote to loop through the information also worked. Now, on Wednesday, I showed you how we might write a piece of code that we may want to use more than once. Now, this piece of code here, I'm expecting to use more than once, because I have a feeling that every time the scores change and things like that, I would want to print out the scores. So I don't want to be copy-pasting this code around the place. Instead, I would like a function that prints out the players. So I'm going to have a function. It's going to be a void function, because I know that I don't need any information back from it, in the same way that this isn't changing any variables or anything, so I know that no information is coming out of this bit of code. But what's happening is it's going to display stuff onto the screen. So in order to display stuff, this thing is going to need to know the array that contains the scores. I'm naming this really specifically, because I don't want you to think that this is the same variable as this. This variable is going to get put into the function, but the function itself is going to have, like, kind of in a sense, its own version of it. So int score array, and I'm going to use this as well, int length, for me to know how far to go into that array to print out. There are options here. If I wanted to, I could just use num players inside the function once I write the function. But what I'm going to do is write a generic looping thing that will work for any array. So that is my declaration of the function, so that I know that I can use it in here. And then I'm going to write the definition of the function here. So when I'm writing a function, I always understand that if someone's going to read down here, they're not going to know where this sits in the main, and so they're going to have less context for why it exists. So because there's less context for why it exists, I should explain it here. We'll print out the scores of the players in order. will not change any values in the array. Will print from the start of the array until index length -1. I'm being really, really specific here. So this is like showing exactly what's going to happen. Because if I wanted to, I could say just print out the first 3 players, and I could give this function a different number, and then it'll only print out some of them. I love how also I'm talking about this function as if it already exists. It doesn't exist yet, but I have a clear idea about what I'm going to do with it. Okay, so first thing I'm going to do, this isn't necessarily going to work, but I know that this is the function that I want to put into this. This is the functionality, I'm going to be clear, functionality that I want to put inside this function. So I'm going to copy this. Actually, I'm going to cut it because I don't want it in my main anymore. I want it in here. So let's have a look at which parts of this I'm going to need to change. First of all, I do have access to num players, so I would know num players here, but I've decided that I want this function to work with lots of different arrays, not necessarily arrays that adjust through the number of players. So I'm going to say length here. So I'm going to say that if you want to call this function, you have to tell me how big the array is that you're working with, and then I will use that. This printf should work the same, except we are not using this array. Remember what I was saying, what goes on inside the curly brackets stays inside the curly brackets, which means I am inside this set of curly brackets here, not inside this set of curly brackets. Even if my function is called within this set of curly brackets, I will not be able to see this variable. So I cannot see this thing called scores, so I can't access it, but I have my own here called score array, which may end up being the same one because that's what I'm going to pass into this function. But I want this function to be able to work with like multiple different things. So let's say I had 2 teams. So I had scores for the red team and scores for the blue team. I would be able to use this for either team because I'd be able to say, all right, I'll give you a score array, and this time it's the blue teams, or this time it's the red teams, and I can work with either one. So that's why I'm not trying to reference this thing, but I'm trying to reference its own one. And when I call the function, I tell it which set of scores to work with. So score array is a variable that sits inside this function. Length is also a variable that sits inside this function. And we'll loop through and print everything out. So save that. And to test whether this is working, I will call the function. So to call a function, to ask the function to run, we call it by name. We should be a little bit familiar with this because we've done this stuff with printf and scanf, but we've put different stuff in the brackets with those to make them work. So the first thing that goes in the brackets must match the type of the thing that this thing expects as the first thing in the brackets. So it's expecting an integer array. I do have an integer array here called scores, so I will put its name there. Question I get a lot when I do this is, how come it's not this? Or how come it's not this? Anytime I put square brackets after an array, that's me saying I don't want the array. That's me saying I want one part of the array. So if I did this, this will put a single integer in. I don't want a single integer because I've got the square brackets here saying I want the whole array. So if I want the whole array, I give it the whole array, which is just the name of this entire variable. The square brackets after I've created the variable give me access to one element at a time. So that's why there's no square brackets when I'm passing the whole array into the function. And then I need to say, how much of this array do I want to print out? I'm going to use the num players here to say, I want all of the players in this array to be printed out. Okay, so this is the kind of thing that we do with functions. We declare that a function exists so that we can use it, and then when we use it, the program knows to jump to wherever that name matches, and then set up its own variables based on the things I gave it, and then go through them. So let's see if this works. I'm going to save it, compile it again, using my up and down arrow keys here to be able to access previous commands. And I'll run the score tracker. Awesome. We are getting, from the outside, we can't see the difference. Same behavior, because we used pretty much the same code here. But the trick now that we're getting is this code here, it wasn't super clear what it did, right? So we had just had the loop in there, and it was just this stuff. But now, we can read through our main in English. Because I can just go print players. Oh, cool, this thing's going to print players. I'm sure there's some detail of what it's doing, but I don't know. Don't have to look at it. I only have to look at it if I want to change the way it prints. Otherwise, I read this in English and I assume that it's going to do a good job for me and just let it do its thing. So that's one of the beautiful things about functions. Also, if I want to print players more than once, I can just call this function again. And so me doubling up on code is just one line rather than having to copy paste this whole thing. And now also, if I realize there's a mistake in this somewhere, I edit it and it's only ever once in my code. That's like some of the power of functions like that. Okay, let's go back to this. So I've taken this, modified it, and I made it into a function. So we've got our array, and it's got some scores stored in it. The scores that we have in our code are slightly different. That's fine. We could think of the game changing over time and people's scores changing. So let's look at the two things that we were asked to do. We were asked to figure out who's currently winning the game. And we were also asked to figure out what the total score is of everyone in the game to see if, I don't know, if the players have reached some kind of threshold which changes the phase of the game or something. Like, I'm just making stuff up here. It's not super important. What's important is we learn how to work through the arrays. So let's go for the highest first. So if we want to find a particular value in the array, and we know that there's some kind of condition that that value must be, we can do this because we know that a loop through the array is going to be able to see every value in the array. So if I know that I can go through and see every value in the array, I definitely have a way of finding the highest. What I'm going to do is say, what's the highest value we've seen so far as we go through? And we'll look at each one of them and go, are you higher than the highest we've seen so far? If you are higher than the highest we've seen so far, you're the new highest. And then I'll go to the next one and go, are you higher than the highest we've seen so far? And it's like, oh, no, you're not higher. I go, all right, the highest we've seen so far is still the value we had before. And I'll go on to another one, and maybe this one is higher. And I'll go, okay, this is higher than the highest we've seen so far. It's the new highest. And if we get to the end of the list doing this, no, end of the array, sorry, it is a list of numbers, but I'll use the technical terms, the array. When we've reached the end, we've checked every number against the current highest, and the one at the very end should be the highest against everything. So, got some code here, but let's do it rather than just looking at it there. So what I'm going to do now is I'm going to go straight into a function. I'm not going to write it in my main at all. Let me see if I want to do this. Yeah, okay. I'm going to do this as another void function. And it's going to just print out the highest. So it's not even going to keep the highest. Yeah, I think so. Or maybe I should do a function that returns something. Because I think this would be interesting, right? Let's do, instead of print highest, we're going to do find highest. And if this thing is going to loop through the array, it needs to get access to the array itself. So we're going to call it score array again. This empty square brackets here is interesting, right? Because the empty square brackets says we don't know what size this is. These ones are really specifically saying, okay, it's exactly this big, so make us this piece of memory. This one's saying, this is going to get given to me as an input. So the input is the thing that's going to decide how big this is, which means that this function will actually be able to work with different arrays. So if I had more than one array here, so I had one team had this number of players, and the other team was made to have twice as many players, so maybe they have weaker abilities, but there's twice as many of them, I would still be able to run this function on that array, because this one's not saying how big it is, but it does have... Ooh. Oh, just froze up for a second there. It does have specifically given to it when it runs how long this array is. So this array is going to exist outside, get passed into the function, along with how big it is. Okay, so I'm going to take this, I'm going to copy it, paste it here. So note that when we're declaring it, it just says, all we're going to tell you is the inputs and outputs, right? So give you the name of the function, its output, and its inputs, and that's all we say, but that's enough for us to use it. And then when we're here in code, we're going to say, no, I'm going to give you a whole set of instructions here, so we have the curly brackets for that. Okay, so this finds the highest score from the start of score array to the index length -1. Prints out the highest score, returns, and so this is interesting because you've got to think about how would we want to use this, like under what situations are we going to use this. And there's two things that are going to happen, right? One output goes to the human. That's this printing output. So this is output to the human, and there's no program output. There's no function output to that. This is just display stuff. So we have two things we want to do here. We do want to display something, but we also want to give some information back to the program. So one interesting thing we can do is, what do we think the program might want to know if we're trying to find out who's winning the game at the moment? I don't think the program cares what the highest score is, but the program might care which player is currently winning. So what we're going to do is return the index that the highest score was in. So this might be something that will come in handy at some point, because we can programmatically go, all right, find the highest, tell the players who the highest is, but then we're going to use this integer somewhere else for something else. I don't know what it is yet, because given the amount of time we have, we're not going to get that deep into this demo, but I think that this number might come in handy. If I didn't, then I could do this as a void and go, nah, we don't even care. But I can see a possible future where I might use it. And also I could call this function and just ignore the int anyway. So I can use this either way. So what we're going to do, loop through the score array, check if the current score, so the one that we're looking at, is higher than the highest. If so, replace the highest. So what I'm doing is, you know, I was talking before about writing comments before code. I'm putting my reasoning out first, and then I'm saying, once I've got my reasoning, I'm going to fill it out with the actual technical code. If we want to look at how this thing ought to work, what we could do is we could look at this and we can say, all right, let me set up two integers. So I've got one integer here, which I'm going to call highest, which is going to be my highest value. And then I'm going to keep track of who is the highest by saying index highest. Anyone who's thinking really deeply into this is going to realize that I actually only need the second one of these, but I'm going to do them both for clarity. So, what I might do is think about my game and my assumptions. My assumptions was that everyone started at 0 points, and I'm also kind of assuming that everyone goes up in points. So at the moment, the highest is 0, and the index highest doesn't actually exist, and I'm going to hope that that's okay. So, or maybe I'm going to set index highest to -1 so that if this thing doesn't work, it'll blow up. Like, you know, when things don't work, you want them to not work really clearly and somewhere where you know that something's going to happen. So if I get through this algorithm, this like algorithm is basically the recipe part of the program. If I get through this and these things haven't been set to one of these numbers and one of these numbers, not sure if you can see my cursor there. So if these don't get if this one doesn't get set to one of these and this one doesn't get set to one of these, then I know it hasn't worked properly. And that's why I want this -1 to really like ring an alarm bell, because it should crash the program when I try to do something with it. So what I do is with these two, I look at the first number. So I'm doing the while loop that goes through the list. So it's going to start at 0 and end at 3. So it starts at 0 and says, is 95 higher than the highest? Yes, 95 is higher than the highest. So what we will do is if we pass that test, then this becomes 95, and this becomes the index of where we found the 95. So this becomes 0. Then our while loop continues to this one and says 907, test 907 against 95. I go, well, 907 is higher than 95. So we're going to replace it. 907, and this will now be the index of the new highest, which is 1. We're going to go to this one here, the 2, and then we're going to check it again. I wish I hadn't used so many digits now. And now 1567 is higher than 907, so it will replace it. 1567 will replace it, and this will become the 2, the index here of the highest. And then we move on with our while loop here, and we'll check this number, 732 versus 1567. This is not higher than the highest, so 732 will not replace 1567, nor will the index be replaced here. And so this will be my highest for the list, this 1567 at index number 2. So that's what we're going to do, is we're just going to walk through this and test these against the current highest. And if they're higher, then they get to replace it. So let's come back in here and start to write that code. So knowing that I need to keep track of which one is the highest at the moment, I'm going to have int highest. And I'm going to start that as something that is lower than any of the scores I'm expecting to see. So I'm making assumptions about what this game is here. So I'm assuming that they all start at 0 and then they go up from there. So if they're all going to start at 0, then I can say the highest will start at 0. And the index of the highest, I'm going to do that thing that I did in the image where I'm going to make that a -1 so that if something goes wrong and it's still -1 at the end, then I know, because of that -1, I know that something went wrong. Okay. So I've said I'm going to loop through the score array, so I'm going to do my standard loop setup. I is going to go up until just before length. So I've got my standard loop here, and then these checks are going to happen inside the loop. So I'm going to Control X, Control V, cut and paste these in here. Make sure my indenting is nice as well. So I said check if the current score is higher than the highest. So check if. The keyword is right there. So sometimes when I write it, the keyword is exactly the same word that I'm going to have. So I'm going to say if the current score is higher than the highest. So the current score is this index into this array. So score array I. So as I'm going through the array, this is me going through this array. and saying, I start at index 0 and I look at this number. Index 1, look at this number. Index 2 looks at this number. Index 3 looks at that number, right? So, oops. I'm going to go through, and this is me looking at each of those numbers, and I'm asking, is that a higher score than what I saw previously as the highest? So, the first one's probably going to come true because highest is 0, and we know that all of these scores at the moment are positive. Who knows in the heat of a game if that's always going to be the case, but for now it is. So you can see, actually, as I'm coding this, you can actually see a lot of the problems that can come up. A lot of these things like, oh, I'm assuming this about the game. How do I know that that's even true, right? So there's a lot of little bits going on there. Okay, so highest there. So if it was the highest, this comment goes inside the if statement, because if so, replace the highest. Okay, so if we're going to replace the highest, I'm going to say highest is now going to become the current score we're looking at, and the index of the highest is now going to become the index of what we're looking at. So this is what I did before in these boxes where I said, okay, this one here, then this one, then this one. Highest becomes the number, index highest becomes the index. I++ here. I do also want to just leave some structural comments for myself. So we have checked I scores. So if at any point we're in this loop, we think about the number I, it's going to tell us how many scores we've checked previously. So it's a little way of remembering that like that. When we hit the end of the loop, we can actually say the same thing. These are the assumptions I'm making about my code. Sometimes it's really nice to have these things so when you're debugging, you can go back and go, okay, this is where these things should be now. If I check the variable I anywhere after this loop and it does not equal length, then I know that something happened in here. I made a mistake or something like that. Okay, so if we've checked that all there, we should know what the highest is, which means we should now be able to print out the highest and return the index. So let's do these one at a time. I'm going to print out the highest. Player something has the highest score with whatever score that is. I'll put a new line on the end so that things don't get messy. So player, and it'll be the index highest. I'm going to copy and paste that variable there, and then it's going to be their score, which has been stored in highest. I haven't gone over my line yet, so I'm okay there. I think I'm exactly on 80 characters there. And the thing that I wanted to return, so I've told everyone what their highest score is and who they are, and I wanted to return who they are, the index of the highest score. So I'm going to return highest. Oh wait, sorry, spelled that wrong. I'm going to return index highest. This should give back all the information that I need. So this is exactly the kind of thing where if I wanted to run this multiple times in the program, I don't want to copy and paste all of this code. So anytime I want to find the highest, all I need to do is use that one-liner now. Oops. Find highest. And I have to say, okay, what information did find highest need? It needs the array of scores. And it needs to know how many people it's checking, which is the number of players. So it's interesting that these two are taking in exactly the same information, but they're doing something very different with it. So if I run this now, what I'm hoping will happen, just checking if there's anyone saying he's behind you. No, so that's good. We will... There's a discussion of a Chad there. Okay, I'm going to let that go. This should print out everyone's current score, and then it should print out who has the highest score. And you notice that I'm not even using this integer. I could if I wanted to, so I could do something like int current winner is equal to the result of that. So if I wanted to use this later, I could. I'm probably now going to get a warning that I've created a variable I'm never using, but that's okay. This should print it out as well. So let's test this and see how this goes. Yeah, I got a warning that I set a current winner and I never used it. That's okay because I know that I have a potential use for this in the future. Who knows? Okay, so I'm going to run the score tracker, and it's going to say this was print players, print scores. I think, what did I call it? Print players. I guess it's printing the players and their scores. And then find highest runs. And when find highest runs, it will print out who has the highest score. And we now know in the program, at this point, we have got a variable saying who's currently winning. So we've got a bit of information like that, which is handy. If I wanted to get the total scores, I could do a very similar thing. I'm actually running out of time here. Oh, actually, 6 minutes. Let's code it up. Because it's really similar. It's another function. Total score. And it's going to take the same information in. So I'm even going to copy paste this because all of my functions here are an individual function that loops through the entire array. So if it's going to do that, it needs the array and it needs to know how big it is. So I've just copied this line, everything except for the semicolon, because I know I don't need it. And I'm going to paste that there. And then I'm going to work on my functionality. So the first thing I'm going to say is this... Actually, this is an easy one. Returns the sum of all scores between index 0 and length -1. Yeah, that's actually all it's going to do. I mean, I could get it to print something out, but maybe I don't necessarily need it to print something out. I just want to know the total. So, again, while loop. If I had that macro that just printed out the while loop, that would also be quite good here. But you get used to this. You do get used to typing it out. Except for all the times that I forget to put the I++ in it. I've already done it once in lectures, and that won't be the last time. I is less than length. Okay. I definitely have a while loop that goes through the whole lot. I do want to add up all the scores, which means I need a variable that's outside of these curly brackets to store the total. It's going to start at 0, and then I'm just going to add things to it as it goes along. So I'm going to say total, show you a new shorthand here. Total plus equals score array I. So what I'm doing here with this loop, let me change my variables here to a different set. Actually, not even using this one, because I've only got one variable there. I'm going to call this one total. I'm not going to write it all out this time. I don't have enough stamina to draw things with my mouse like that. So the loop goes to 0 and it's 95. So total starts at 0. And then when the 95 comes in, it becomes 95. So let's just cross that out and go, okay, now it becomes 95. And then the loop goes to 1. When the loop goes to 1, it reads 907. So total then becomes 95 plus 907. And then the loop goes to 2 and it reads 1567, and it's going to add that to the number as well. Plus 1567. I'm going to leak out of the box here. And it goes to this one, it's going to add this to the number as well. So that's plus 732. So I actually have a slide here. It's like, oh wait, that was another new syntax. So let's look at this shorthand operator. Similar to what we did with the plus plus, the plus equals is going to do something that kind of lets us shorten some mathematical operation. So if I have b equals b plus 5, or I have a plus equals 5. These are going to do the same things to their respective variables. So they're just going to add 1 to whatever the current total is there. So this plus equals is like what we would think of as an accumulator. It will just keep adding things to this number. So a plus equals 5, that now goes from 0 to 5. If I then do a plus equals 10, it'll go from 5 to 15. If I do plus equals another 15, it goes from 15 to 30. You know, so anything that we do, the number on this side just gets added to that number and then gets stored in that variable. So we're actually reassigning the value of this variable to whatever it used to be, plus whatever we have here. So the equals is the assignment, and the plus is like we're also adding. So a plus equals 5, b equals b plus 5. Those have the same effect on their respective variables. Not that one, looking for this window. Oh. Hello. Someone's saying hi. So, here we have, this is now going to go through, and it's going to go through the entire array, because we know we set it up like that, and it's going to add to total, and it's going to add the value of each element to the total. So, at the end of this, we're going to give back the sum of all those scores, which is whatever value that total had there. So if I want to, I can do something like this. Printf total score is, and it's a number, and we'll put a new line after that. Check out what I can do here. So as the number that's going to be printed out, I can use integer variables, I can use raw values. Because this is an integer function, I can actually use the function here as the thing that gets printed out here. So I can actually say total score, the scores and num players. This function here, when it finishes running and it returns something, will transform itself into an integer that then will get printed out here. So, did I save that? Let's compile this. Still got the unused variable, still not using it, and run it. So, the first function prints out all the players. Second function identifies the highest score. The third function was finding the total score, but what we were actually doing is using the output of the function. The integer that gets output as the function gets output exactly where the function was called here, and we're using that directly in a printf statement. All right, I've hit 6 p.m. but that's what we've got so far. We have been able to build a program using an array that also has some functions in it, and so hopefully this gives you an idea about how we might use functions and stuff like that. So today we talked about the theory of a computer, so we talked about the difference between the sort of processor and the memory and some of the details, and we also looked at how we can do collections of variables in arrays, and we've got a demo now that is our first use of arrays, but also our first use of functions. And so I went a little deep in there, but hopefully what you can do is, now that you've seen that and you've seen me do it, you'll be able to kind of pick that apart and learn how it works. Obviously, more detail coming in your tutes and labs and stuff. And we've got a little friend here who is saying goodbye at the end of the lecture. All right, so I'll wrap up the official lecture there. Sorry for going a couple of minutes over time, and but I will come back in a second and answer your questions, and Chicken will also answer your questions as well. All right, back soon. Alrighty, we're back. I can fully understand if people are confused at this point, so I'm here to answer any questions that you have. You want me to go back over the code or anything like that and have a closer look at things, because I'm sure that people are going to want a closer look at some of this stuff and a little bit of why it's doing what it's doing. Ryan is asking, when you wrote return index highest, what was the purpose of that? So the purpose of this was that I thought that this function, even though it was giving information to the players or the humans about it, about who is currently winning the game, I could see a potential future where I would want to know in the program here who the current winner is, and then I could do something interesting. So I could do some kind of, I don't know, some kind of status effect on the current winner so that other people score more points for doing things to the current winner or something like that. So it's nice for me to know who the current winner is, even though in my demo here there's nothing that references it, there's nothing that uses it. I just thought that it would be useful potentially in the future to have it. So, I mean, you could definitely say that there's nothing in this program that uses it, but I can think of a potential future where I might want to use it. I might put a comment in here, actually. Right, so I'm just explaining the same thing there, that it's not used in this demo, but if we were going to develop it further, we may have a use for it. Hemi is asking why was the first function using void, but the second function was not using void? I mean, it's a pretty good question. It's actually really the same thing that I was just talking about there. This one's supposed to find the highest, and so we're giving back the index of the highest. But in terms of what we were doing today with it, all we were doing was printing stuff out. So yes, we could call this a void function if we want to, except we can think about a possible future where we might want to use the knowledge that we've gained about who the current winner is. And so if we're thinking about using that knowledge sometime in the future, then we might want to keep track of it. But this demo doesn't do anything with it. So that's the only reason why print players is void and find highest is int. Because find highest is like, okay, we're getting some information, maybe we want to feed that information back into the main. Whereas print players doesn't gather any information at all. So because it's not gathering any information, it has nothing to offer back to the main, so it's a void function. Total score also was gathering some kind of information, and so I chose to do this one in a slightly different format where the integer it gives back is the only thing it does. So total score does not tell our user anything, so it does all this calculation, and then it just gives back the total. So this one is something that when it runs, it's completely invisible to us, and it's only when total scores is used inside this printf that we, running the program, actually get to see what the result of it was. So you can see how sometimes, and this is something that, you know, it takes a lot of practice to realize what you want your output type of your function to be. Because I flip-flopped on this one. I was like, oh, should it be void? Should it be int? Not sure, you know? And that really, those decisions are the decisions you make as you're structuring your program. Sarah's asking, what is int length for? So, each of these functions is going to take two pieces of information. One is an array, so it gets an array, and when it gets an array, it gets access to all the information we've stored in the array. And the length is our way of saying, use the array up until a certain point. Because one of the interesting subtleties of the array going into the function is, let me show you something that I could do. let's say I have another team, and it's a special team that has twice as many players as the first team. So I haven't set anything up for this yet. But what I could do... Ooh, what's happening? I don't know why it doesn't like my space bar at the moment. That is super weird. Yep, don't know what was happening there. Anyway, so I have another one here. And so what I could do here is I could print players for the first team. And then I could print players for the second team. Scores team 2. And this would have a different number of people in it because this team has twice as many players. So I would do this, and then when we go into print players, when I go into print players using these values, this is 4 because num players is 4 at the moment. I can actually change that, but num players is 4 for the moment. And then it gets an array that happens to be length 4 because I've given it this array. It will loop through 4 times. If I give it 8 here, this loop will happen 8 times rather than 4 times. So whatever number I give it for its length is me telling it how many times to run this while loop, because the while loop is I less than length. So it starts at 0 and goes up to length, which means the length determines how many times this thing will run. And if I give it a matching array, so the array is a certain length, and I tell it how long the array is, because actually when you give an array to a function, you're not telling it how long it is, especially because we have not put any numbers in the length here. This function can take different length arrays. So I could put a length 4 array in here like this, or I could put a length 8 array in there, so long as I make sure that these numbers match up in some way, basically so that this length is not longer than the actual length of these arrays. I can use the same function with 2 different size arrays and it'll still work. So there's something kind of cool about that, I think. Yeah, so hopefully... Oh, where are you going, kitten? She's trying to decide where she's going, but she's definitely saying hi, but she's trying to figure out where she wants to sit. What are you looking at? Okay, so yeah, so that's why we have the int length. The int length allows us to choose. Just make sure my face is still here. Allows us to choose how big the array is when it goes in, and it means that no matter what different arrays we might create here, we can use this function for any of them. So it's actually slightly different from what I've got on the slides, if I remember correctly. I think the slides was just like really locked to the number of players. Okay, I'm going to delete this because we don't need this. But hopefully that answers your question and gives you an idea of why we're going to do that kind of thing. Okay, Jennifer, sorry, I made that mistake last time. Jennifer is saying it lets the function use num players as the endpoint of the loops. Yeah, exactly. I think you're answering Sarah's question there. Ryan is saying, still a bit unsure about the function of the return function. Okay, let's get our terminology exact here. We're saying, what does the return keyword do? So the return keyword, if we remember from the slides on functions that we did on Wednesday, the return is going to end this function. So it's easy when the return is the last thing in the function, because the function was about to end anyway. But what it does is it takes a value from a variable in here and it gives it back so long as that's the right type. So this is the right type here. Index highest is an int. And then what it does is it says when this function runs, it's going to take whatever value was in here and it's actually going to say the entire function. Where did we call it? Here. The entire function here, when it's finished, is no longer going to be a function. It's going to be that integer. So what happens when this thing finishes running is the highest... Oh, this is the total score. What was the total score? 3301. So what actually happens here is kind of, it's kind of like this. After this function's run, it replaces itself with whatever it was returning. So wherever it was, here, becomes this number. So I'll put that back the way it was. So you can think of it like that. When this function finishes running, so it finishes running when we say return, and if return gives it back a value, that is the value that, if we were to read it line by line in our code, that value replaces the function call. So the thing where we called the function here, and then can be used in other things. So we can have the return of a function be placed in a variable, or like we did here, like this is what we did here. We took the return of this function and we placed it in this variable, and this time we took the return of this function and we used it as a number that we were going to print out. So the return is like saying, we've done some calculation and this is the thing that the function transforms into, because the function actually had a type, which meant the function always said that when I finish running, I'm going to turn into this type of variable, in a sense. So hopefully that helps with learning about returns for Ryan. Matthew's saying, functions with side effects that aren't obvious. Yeah, so you can have functions that do things, but you may not know exactly what they're going to do. So this one's like, it's not really doing anything, but it's returning something. This is a function that has two kind of things that it does. So one, this is like what we would call a side effect of a function, because it's not the main transformation of the function, which is like what it returns as, but this is another thing that it will do that will have some effect that we'll see happening. So we can call all the printing in these side effects, and then we can call the actual return here the result, I guess you could consider, of the function, which is interesting because this one has no result. It doesn't change itself into a number or anything like that. It has no output. It's a void. But it does have a very important side effect that we're going to use, which is printing out the number of things. So this hopefully will show you the value of a void function. Sometimes this side effect of what it can do is more important than what information it could give back to the program itself. So giving back information to the program is the kind of thing I was talking about, where you take where the function was called, you transform it into a value of the type that the function is. Magic is asking, sorry, I'm not getting why it's index length -1. So here we said we'll print from the start of the array until index length -1. So let's have a look at our diagram again here. And I'll pick another color. Our length is 4. Because we know that because num players is 4. We made num players equal to 4. And every time we passed our length into here, we were passing in the number of players, which is 4. So if I say I'm going to print out from the start of the array until index length -1, then I'm printing out from the start of the array 0. This is length -1. I'm printing this out, but I'm not going to try to print out index 4. Because index 4, no, does not exist. And if we tried to print out index 4, we'd cause problems. So that's why I'm saying index -1. We don't try to do anything with index length. We do length -1 at most. So you can kind of see that here, where length is 4. But there are 4 elements, but we're never using the index 4. That's why I'm saying index -1 there. Oh, Magic was wondering where that was declared. It's kind of interesting, right? Because it's not really declared. It's just the nature of the arrays. Because the array index... Let me get my cursor back over here. The array indexes tell us kind of how to access things in here, and they tell us by distance from the beginning. because this one's at the beginning, its distance from the beginning is 0. This one's at the end here, its distance from the beginning is 3 because you had to hop over 3 things to reach it. So there's this kind of thing where you need to think about, if we start at 0 and something's of a certain length, then we only have data up until length -1. Yeah. So as magic, as you're saying there, I have to remember the index 0, definitely. That's how it works. It's just a new way of thinking about things, and it's kind of funny and odd, but you can kind of see how when I'm running loops, I'm thinking of the iterator, the I, tells me how many times I've previously been through the loop, and that could come in handy. And starting that thing from 0 and going through matches up with this really nicely, so we can go through. So it starts to become second nature, but at the beginning it's kind of like, oh, why are we starting on 0 instead of 1? But after you get used to it, it starts to be like, okay, I can see how I would use this. Yeah. Okay, Feo Mars saying, on line 24, why do we write scores inside of the brackets instead of writing scores with brackets? So I did say this, so if you do need to go back, I did talk about this as I was doing it, but I will say it again now just so that you can get a good idea of what's going on. So scores here. Let's draw this. So I've run out of colors. Okay. So this is scores is this. If I do scores with a square bracket, I mean exactly one of these only. I won't get all 4, I'll only get one of them. So if I do scores with a square bracket, I have to put a number in it. So let's say scores 2. Is just this individual element. If I do scores with a square bracket and nothing else, then it won't be able to read it. Because this is inside code that's actually running. Anything with the square brackets in here says I'm trying to access an individual element, as I'm doing here. Anything with a square bracket after it's been created accesses an individual element. The awkward thing is up here. We have the square bracket because this is a type. So this is us saying, I want a particular kind of variable, and this is my way of saying, I want an integer array. In the same way that when I'm creating something, I want an integer array. I can, even when I'm creating arrays, this is like one of the other ways we can do it. I'm going to call it score. Wait. I'm just trying to think of a good name for it. I'll do it afterwards. Scores 2. That's a bad name, but you know. If I wanted to, I could do this. And then I could do this array would actually get created exactly big enough to hold all of these. So this array gets created with length 8. I think that, yeah, I typed in 8 numbers there. So this is a way that we can create an array without actually needing to know how big it's supposed to be until we just chuck the data in. I'm not too big on this way of doing it. I think doing it this way leads you down a very dark path of not actually knowing how big your arrays are. So I don't use this at all because I consider it dangerous. Like, it's not super dangerous. Like, C is going to be able to deal with it, but I don't have this constant here that's really strongly defined as going to be how big my thing is. I now have to remember the number of things that I put in there, and I have to use this 8 everywhere else I'm doing stuff. So I consider this way of doing it super dangerous. But you can see how this thing here says I am an array, and I don't know how long I am. So this is saying you need to put in an array, and it doesn't have to be a specific length. It can be any kind of array. And then when we put the array in here, We're using it like a variable. So the entire array is one variable, and the square bracket says I want a single element inside the array. But if I use no square brackets, I'm saying I want the whole array to go in. So the square brackets, after you've created it, accesses just one element at a time. Hopefully that answers your question, and clarifies it for other people as well, because I think this is something that definitely does need to be clarified, and is something that you'll kind of get as you keep going through with practice in the tutorials and stuff like that, because otherwise it's pretty hard to keep track of this. Okay, hopefully that helps. Yeah, all G, great. Jennifer is saying length is the number of elements. Oh, you're answering stuff. Thank you. That's great. Yeah, you were answering Magic's question, I think. Sarah is saying, for the int and void part, does it mean the calculation we use int, others will be void? Not sure exactly what your question is necessarily there. I'm going to get rid of this because I know that this is bad code and I don't want it to be in the demo. Are you talking about these, Sarah, when you're asking about the int and void? I think that you might be. So this means that print players, when it runs, when we call it as a function, it doesn't give us any information back. So I can't do something like this. Because it's a void function, I cannot assign the function to a value to put into a variable because it has no value. However, if something is an integer function like this, I can expect it to have a number at the end that I will then put into a variable like this. So this one says I don't give you any information back. I don't make a number or anything, so you can't store the function in anything. But this thing says find highest is going to give you a number back, so I can literally take find highest and store it in a variable. Find highest is guaranteed to us because it is an integer function. It is guaranteed to us, well, if it runs correctly, it is guaranteed to us that it will give back a number, and I can store that number. Sorry, better than a number, it will give back an integer. If it gave back a double, then we'd have other issues, but it gives back an integer. Yeah. So that's the difference between a void function and an integer function. Integer function says, you can run me, I will hop over into my code here, I will go through my code, and I will return something, and that return is something you will then be able to use, and I will give it back at the line, in the position of the line where I was run. So this is where the integer will appear, and then this line, the rest of this line, which is the assignment with the equals, will run as if the result of this function is just an integer just sitting here in the code. Yeah, so if the function is going to make a number, it's a good way of thinking of it, actually. I like the way you're saying it. Yeah, if this function is going to make a number that we want to use, then this should be an integer function. If it's not going to make any numbers that we can use, print play is literally not making any numbers, right? It has an I, so I guess it is making a number, but it's not a number that we care about afterwards, so it should just be equal length at the end. That is a void because we're not using that number, whereas this has a valuable number to give us. This one also has a valuable number to give us that we're going to use later. Alrighty, I think we have cleared up all of the questions that people are asking at the moment. I'll give you a couple of seconds to ask one last question if you want, and we can pat chicken in the meantime. And if not... Oh, Miss Belt is asking, who do I contact to ask for an extension of the lab? If you need an extension for the labs, if you have any issues with submitting or anything like that, talk to your tutor. So your tutor is the best person to talk to about that. If you have a serious issue, though, I encourage you to talk to special consideration, because if it's a serious issue that's going to impact more than just your labs and stuff later on during the term and stuff, it's better to get official special consideration, because then we can give you extensions, like longer extensions on assignments and stuff, and give you special provisions for the exam and things like that. But if it's just like a temporary thing, it's like, oh, I've got a problem, you know, my computer broke, but it should be fixed in a couple of days, then your tutor can just give you, like, you know, a few days extra for your labs. Jennifer says, since you mentioned that Chicken will be taking questions, here's a question for Chicken. Master Chicken, what is your wisdom? What is your wisdom, Chicken? Do you have anything to say? Nope. I think her wisdom is to receive pats, sit on warm mouse pads, and generally don't have to do anything. Okay, we're gonna wrap it up there. Thanks everyone, and I will see you next Wednesday.